So if we explore these relationships between the original function, the first derivative, and the second derivative a little bit more on the next page, page 241, these are all the same characteristics that we've been dealing with throughout this year, but if we apply these characteristics to the second derivative, then instead of f of x having these results, then f prime would have these results, because I can literally take one prime mark away from the second derivative and take one prime mark away from the first derivative, and notice how this would match the regular characteristics that we've been talking about all year. So if we have the second derivative having these characteristics, then the first derivative would have these results. What's new then, that we're going to discuss more in this section and the next one, is what do these characteristics from the second derivative tell us about the original function. So previously we mentioned how this is that idea of concavity, or the curvature of the graph, be like looking like a regular parabola or an upside down parabola. So if we let the second derivative be 0 or undefined, instead of classifying that as a critical point, okay, where we have a potential max or min, okay, maybe we'll label this critical point, f of x, we'll say, has a potential inflection point. And this is what I sometimes refer to as a PIP, kind of cute, potential inflection point. So instead of being a critical point like the first derivative gives us for increasing and decreasing, then we could have a PIP, or a potential inflection point, for the original function. So if the second derivative is positive, that's telling us that the original function is concave up. I'm going to abbreviate CC for concave. If the second derivative is negative, we know the original function is concave down. So concave up, similar or looks similar to a regular parabola. Concave down looks similar to an upside down parabola. And if we have any change going on, it doesn't really matter if it's positive to negative or negative to positive, then we can clearly classify this PIP, okay, a possible inflection point, as an actual point of inflection. So it really doesn't have the distinction of max or min like we've said previously. In this case, it either is a point of inflection or it's not. So it's not a specific type of inflection like a max or min is a specific type of point. So we're going to go ahead and look at these connections a little bit further, dealing with the same function that we did on the previous page. So this is the original function that we looked at previously, and we graphed it on the calculator, and we found that this was the first derivative. So we're going to go one step further. Okay, we're going to find the second derivative, and now we're going to determine the intervals of concavity. So where is this original graph, concave up, concave down? If it changes concavity, then we definitely know we have a point of inflection somewhere. So let's go ahead and try to find the second derivative. Now, I highly suggest rewriting this just like we normally would for any function to help us find the derivative. We can take the 2/3 and write that as a coefficient out front. And this x plus 2 to the 1/3 power, let's bring it up and make it negative. So it looks like we're going to have to do a chain rule to help us find the derivative. We'll bring down the negative 1/3, and we'll multiply it by our coefficient. So we'll get negative 2/9. We'll keep the inside. If we subtract 1 from the power, it'll be negative 4/3. And finishing off the chain rule, we got to multiply by the derivative of the inside, which would just be 1. So if we clean this up, definitely going to have a fraction because of a negative power. I'll go ahead and move that down and make the power positive. And we'll have a negative 2 up top and a 9 down below. So just like we would normally analyze for critical points, we're going to go ahead and set this equal to 0 to see if we get any x solutions from that. But we also have to pay attention to if it's undefined anywhere. Okay, so do we have a hidden, if you will, point of inflection, or PIP, or possible point of inflection, or a critical point, however you want to look at it. So clearly, if we multiply this denominator over, we'd get 0 equals negative 2. So by setting it equal to 0, we're not getting any possible inflection points that way. However, looking at our second derivative, it is a fraction, so we have to pay close attention to where it would be undefined, and that's specifically at the x location of -2. So we'll go ahead and label this as a possible inflection point for our original function f of x. So we'll go ahead and perform a sign chart just like we normally would. We're going to go from -infinity to +infinity, breaking it up with this possible inflection point this time. And now we're going to use the second derivative to help us figure out positive or negative signs here. So if you pick any number in here that's going to be negative, we'll go ahead and plug it in. Maybe -3. -3 plus 2 is -1. If you raise that to the fourth, it'll be +1. Cubed root that, it would still be 1. So we're left with -2 over 9, which is negative. Similarly, if we plug in something in the next interval like 0, we'll have 2 raised to this power, which would be a positive number, times 9 is still positive, but we'll have -2 divided by that value, so that is still negative. So looking at our sign chart, we do not have any sign changes, so that means we do not have any points of inflection. And looking at the signs more specifically, it looks like we're concave down on these specific intervals. So we'll say f of x is concave down on -infinity to -2 and -2 to infinity because the second derivative is negative. We can also say the original function is not concave up because the second derivative is never positive. We could also say something like f of x does not have a point of inflection because the second derivative never changes sign. So it's a very similar analysis to what we've been doing with the shear, just we're using the second derivative this time instead of the first derivative, and we have to be careful the connections now that the second derivative has to the original function. We're dealing with concavity, okay, curvature, not just increasing and decreasing anymore. So if we take a look at the graph that we did on the previous page, just to see if this makes sense, notice how from -infinity to -2, we are concave down. We kind of have that upside down parabola type shape. And even from -2 to infinity, okay, we are still upside down. We have that concave down curvature. Now we cannot count -2 because it's undefined there. Okay, we have that sharp point. So you don't have any concavity at that spot, but notice how you are concave down on either side of it. So it looks like the sign chart that we did is correct, and we have the appropriate conclusions based off of that sign chart.